Okay, as is sometimes the case, I've been working on making these how-to videos over the past couple weeks or so, and just working with it. I find things that need to be fixed, and I've already found a bunch of stuff that I fixed. So I'm gonna have to subsequently re-release LaserBoy pretty soon. I haven't even really gotten into the idea that the menu system has changed. I mean, it used to be tab and you'd go right into settings. Now it's tab and you have a menu of settings menus, and each one of these is kind of divided logically into what aspects of the application they are associated with. So that's a little different. And also, just recently, in the language of the LaserBoy Liquid Math script itself, I realized that my naming convention wasn't quite right. I mentioned spread, rotate, spread scale, and there's also a spread move. Okay, those still exist. LaserBoy will continue to be able to read those operator names, but I came up with a better way to name them. Since we'd already discussed in this one, this is the turkey thing, rotating, swish. We had this to do the expanding thing like this. We had start at factor and go to factor underscore within the interval of the frame. So that this underscore here notation indicates the last point within the set of vertices in a frame. Okay? So I thought, okay, well, I should play that through the language all the way through. So instead of spread scale, now it's scale underscore, which means scale from factor to factor underscore throughout the vertices within the frame. Okay? And also then there's the corresponding spread rotate, which is a little different because, in the spread scale you have scale from here to here. And the reason there's a from here and to here is you can't assume that from here is 0 or 1 or anything else. You could put a factor in to start and a factor to end with. So you could go from -1 to +1 and the whole thing would go like that. So to give you that ability in this one, there's factor and factor underscore, which means start at this factor of multiplication for x, y, and z, end with this factor of multiplication for x, y, and z within the vertices of the frame. And then there's the rotate, which, okay, not only does it also use this fulcrum thing, which is a parameter, and rotation, which is how far to go, but you'll notice there's no rotation underscore, and that is because it is assumed that you start with an effective rotation of none, meaning you've already got the frame set wherever it is, which is a set of individual frames, and in each individual frame there is a set of vertices. So you assume that, okay, you're starting there and you're going to the rotation that you want done. It doesn't really make sense to have a beginning rotation, because if you wanted a beginning rotation, you could just rotate the entire frame that way in one step and then start from there for the next rotation step, right? So there's only rotation, there's no rotation underscore, and also there is also a move underscore, which used to be spread move, and instead of rotation you would set a parameter called displacement, and displacement means starting at the origin, displacement is somewhere away from the origin in x, y, and z. And so when you do a spread move, you start with wherever your figure is and you smear it, sort of like slide it towards destination. Okay, and that would be a move underscore. Also, there are corresponding animated versions of all three of these. There is an underscore rotate underscore, there's an underscore move underscore, and there's an underscore scale underscore. And we'll get into that a little bit later, but basically what it does is it uses, there's actually like four state situations to consider. There's the initial state of the vertices in a frame, where, you know, at vertex 0 to the final state of the vertices within the frame. And then there's that concept moving down through the frame set, which gives you the underscore versions of them. And, well, the trailing underscore versions. You have, so for factor, as an example, in right here, there's factor and factor underscore. These would apply to the first frame in a frame set. And then the corresponding versions of them that begin with the underscore, these pertain to the last frame in the set of frames. So when you call this leading underscore scale, trailing underscore, essentially you're saying, I want to use the version of scale that used to be the spread scale, meaning distributed through the vertices within the frame from factor to factor underscore, but I want to spread that effect through a frame set, which means it begins with an underscore, and you end up with the final frame parameters that are associated with that. Okay? And the spread move and spread rotate, again, they don't have there's no rotation underscore, but there certainly is an underscore rotate, and there's even an underscore fulcrum, and there's also underscore rotation acceleration, and then the effect itself is the underscore rotate underscore, which means that from the first frame parameters here's the first frame in the frame set, here's the last frame in the frame set, and when you call this effect underscore rotate underscore, it basically distributes the change in effect between these two situations, a first frame and last frame in a frame set. Alright? Kind of complicated. When you actually see it in practice, you see it in a script, you see how it works, it actually makes sense. It's kind of like when we just did the plain rotate deal in this one. Remember, we just called here rotate with no trailing underscore. Beginning rotation, ending rotation, which was one full rotation around Z. The animated version of that essentially said, okay, we start with no rotation in the first frame and we end with a full rotation in the last frame, and you get the whole one rotation around the 500 frames that are in this generated frame set. Okay, so it's like that. It distributes the rotation through the frame set because of the leading underscore, and if it had the trailing underscore, each one of them would do a spread rotate within each frame. Okay, that's what that's all about. All right, complicated enough as that is. We only looked at the oscillator, and we looked at polar, and we looked at the Lissajous. All right, this generates the circle if you use sine and cosine. Of course, you can use different frequencies and get all those weird Lissajous patterns and stuff that this does. Each one of these things is essentially it's a parametric expression template, and each one of these uses some parameters in that template, and they all are based upon start through duration in iteration steps. So each one of these generates a single frame with initial frame parameters that go into it, right? And they use varying amounts of these parameters These don't use any LBOs at all. These use either simply ratios like a numerator and denominator, or they'll use circular radii to define the size and of the gears in spirograph and where the pen goes pertaining to the center of each gear in spirograph. That's what these do. And then we have all of these things that use LaserBoy oscillators. They use from 1, 2, 2, that one's 2, this one's 3, it's just X, Y, and Z. Lissajous is the same as oscillator XY. It's the same exact thing. If you call this or this, it's the text reader, the LaserBoy text interpreter just says yep and does exactly the same thing. This and this are also exactly the same thing. I just named them that way because of the way I named these other things that are also generators. Okay. Harmonograph actually uses 4 of them, and Harmonograph XYZ uses all 6 LaserBoy oscillators. Okay, and then Amplitude Mod uses 2, Amplitude Mod XY uses 4, because each one of these, see, this amplitude modulation is LBO1 multiplied by LBO2, and it just shows you what that looks like across the, X is time, and Y is amplitude modulation of LBO1 onto LBO2. XY is kind of like the Lissajous thing, except it is amplitude modulation between LBO1 and LBO2 in X, and amplitude modulation between LBO3 and LBO4 in Y, and then similarly there's the XYZ version, and this also uses 6 LaserBoy oscillators. This uses 2, this uses 4, this uses 6. This uses 2, this uses 4, this uses 6. Okay? And then this uses 1. We saw that one. This uses 2. It's basically LBO1 plus LBO2 around the thing. And then amplitude mod is when you multiply the 2 of them together. And then frequency mod is when you actually use LBO2 to modulate the frequency of LBO1. And phase mod is when you use LBO2 to add to the phase of LBO1. And all of these things generate a single frame based upon the parameters that you set in LBOs 1 through 6, and from where you're starting, and the duration you're going, and in how many iterations you do that. All right. All of these also have corresponding underscore generators, and all of these that begin with an underscore create animated frame sets of these parametric expression templates. Okay? And so if they begin with an underscore, not only do they make an animated frame set, but they also require both the initial frame parameters to be set if you want to be from different from the default, and then the final frame parameters are set. So you would be using the underscore LBO 1s through 6 as the final parameters for all of these that use between 1 and 6 LaserBoy oscillators. Okay? So that's kind of how the notation works, and that's why I made the change that I mentioned earlier. One of the files that you get with the LaserBoy examples is called generators still, and this is in fact one example of every generator of all of these, except for these. These are kind of a special version. From here to here, these are different, because all of these actually use sine and cosine to do what they do, which is these are basically the spirograph figures in math. Okay, I thought, okay, they're just using sine and cosine, so I'm not going to mess with that. We'll leave them the way they are and the way they work. So you can set the radii of the gears and all that junk, and they work exactly as they're supposed to. And then I thought, well, if I'm using sine and cosine to do these, it might be interesting to use a LaserBoy oscillator instead of sine and cosine, but set it up so that the LaserBoy oscillator by default is sine, and LaserBoy oscillator with a phase of 90 by that change is the cosine. I did these based upon the values of LBO 1 or LBO 2 or whatever they are. You'll see them in the template things, because there is a file that's just about these, and there's examples of each one of them. All right, so then like I said, from here to here, uses between 1 and 6 LBOs, and here's generators still, and this is an example of each one of the generators. Okay, this is still generators. And as I mentioned before, when we talked about the LBO phase being in degrees, so you could set it to 90 degrees and go like that and make it cosine, this is why all of these parameters are currently remmed out here, because these are the default values. They're just here so you can see them. Phase cycle is 360, which means it takes 360 to go around the circle one time. So that means you can express in degrees, because 90 would be a quarter of the way around. This rotation cycle, you remember how we did the rotate this way and then the rotate that way and so forth. Rotation as a parameter is in cycles of one full rotation. Okay, you could put 2 pi in here if you wanted to, and it would be in radians. Okay, same as the interval cycle. This is where you start on the real number line, you go for duration on the real number line, and it is in units of whole cycles of 2 pi. And you can change these to whatever you want. You already know what iterations is. I've remmed this out temporarily. Still frames is, we already looked at that. This is, so you would just get 25 copies of each one of these still frame generators. This normalized frames individually and then normalized frames with origin. We kind of touched on this. If you set this to 1, it would put the unit circle in the center of space always. It wouldn't matter if everything was over here. The unit circle would still be at the origin and everything would be over here. Okay. Include unit reference. We already know what that means. I'm going to take this out, right? This normalized frames individually is kind of weird. If you make an animated set of frames and it starts with something that's very, very small, like maybe, you've multiplied everything in the frame by 0, it would be just a point, and then it, goes like this. If you normalize frames individually, it won't matter what size each individual frame is through the animation. It will scale whatever's there to fill the frame. So it creates some very strange effects when you do that kind of thing, because it seems like an object is actually changing size relative to space. It's bizarre. So anyway, just to show you, these are some of the things that you can, these are like directives that you can set that pertain to the way this file gets rendered. And we talked about hue span factor. That means how many cycles of the palette of hues you're going to use to go through the entire set of 7,200 iterations in the frame. And hue shift is for each frame in a frame set, the next frame jump that far forward into the palette. So it makes the palette cycle through the vertices in a frame, and this would be moving at 60 palette locations per frame out of the whole palette of 1,530 different versions or variations of hue. Okay, so let's go ahead and render this. And it looks like this, okay? And there's one example of each of the generators, single frame generators, that's there, that's all of them, in the set. And if you look through here, you look at the still frames, or generators still.txt, excuse me, generators still.txt. You can see each one of these. I'm setting the parameters here, and I can set the duration to whatever I want. Remember, that would be from 0, because start isn't here, but by default it's 0 to through duration, right? And then this is all remmed out, so LaserBoy just completely ignores this, but it's here for information. You can look this up on Wikipedia, and it tells you all about the Rodonier curve. And then ratio is calculated because I didn't want to have to keep calculating it over and over again in these expressions. But these are in fact the expressions that make x and y. Then this doesn't do anything except it's here for you to see it. This is where the generator is called, which generates the single frame, puts it in a frame set into the registers, and then color span hues is called upon that, which puts the palette of hues through it, and then render. It's rendered into LaserBoy space, so you can see it when in the running application. Now, what's interesting about this is a complete concept right here, meaning we have our parameters are all set, we call the generator, color it, and render it into space. All right? And it has nothing to do with this one here, which we're calling a generator. Well, we're setting the parameters, we're calling a generator, coloring it, and rendering it into space. And so you get, you get this frame, and this frame, and this frame, and so on. And see, they all have 7,200 vertices in each frame. Okay, so each one of these is isolated in a sense that it is in its own three-dimensional space. Therefore, whatever size it is pertinent only to itself, because of it. Render is being called here right after we call the generator. We're color it, render it. Okay, and what I mean by that, I'll show you. If I go back up here and I say include the unit reference, now we know what the unit reference is. It is the unit circle. It is 1. It has a diameter, a radius of 1, so we know how big space is. And so now we have unit circles. For the first figure, this pretty much takes up the whole frame. It's the same size as the figure we drew. All right, this one, see how this is the unit circle. See, it's this small because this is the figure that we drew, and that would be the epicycloid. Okay, and this is the actual parametric line equation for the epicycloid. And this is where you have, if you know how spirograph works, this would be the equivalent of taking a very small gear and tacking it onto the paper in the middle here, and taking a much larger gear that's, well, pretty much this diameter right here, and working your way around with the pen, right? So this is that's a unit of 1 right there in three-dimensional space, and this is how big the thing ends up being because of this going around it that way, because you're on the outside of the whole thing essentially. So there's an example that these two things are in very different spaces, right? There we go. Okay, this one here is the size of the unit circle, and this one here is probably, I'm going to guess, on the order of 13 times the size or more. Well, no, it'd be more. It'd be like 14.5 times the size of the unit circle, right? See it? And then we, because we render here, we're done with that. We render here, we're done with that too. Now, if I wanted to call an operator that used what was in registers A and registers B, I could do that. I could like add them together or multiply one by the other right here, which would generate another frame in a single frame in a frame set and put it into the registers. But nonetheless, this is something that's important to note, is that when you render like this, you're done. If you call another generator right here, you're in new space. The only time the spaces are relevant is when you use them together in some way. And LaserBoy, by the way, has directives that allow you to keep adding, you can just keep stashing frames into the list of frames that exists outside of the registers. And then you can say, okay, I'm done stashing frames over there. Take that whole thing and join them all together into a frame set, one right after the other. And then normalize that whole thing in the same three-dimensional space and give me that. You can do that. That's part of the language as well. Okay. Wow, we've covered a lot. I think I'm gonna call it. See, right? All right, one more thing. Okay, you remember in turkey.txt, that's where we made the swish, stored it, then we made the that rotating like flower thing that did one full rotation, and then we said, okay, move that along swish, and we did that with this. We recalled swish from the storage list over here back into the registers, and we said add, and it's just add. There's no underscores involved with this. So what that means is this is, okay, whatever we made here, which is that expanding flower thing that does one full rotation, we bring this back into the registers, which is one single frame in a frame set, and we add this one single frame to every frame that was in this frame set. And it's add. So we do the same thing with every single frame in this frame set. We add this to it. And what that means is, I mean, it's literally taking the XYZ values of the animated frame set of every frame, and it's adding a corresponding XYZ value to it, which displaces it somewhere in space because you changed the coordinate location of it by adding something else to it. And it does that by adding this one single frame to every single frame that's in this frame set. To give you an idea what that looks like, let's just go ahead and render so we can see where we are. We did this, so we'll do a render there, and we're here, so we'll do a render there, and the rest of it we know what it looks like. So let's look at this. Let's go and 3, 1, 2, whoops. There we go. All right. There's the swish. There's the rotating, two-dimensional, expanding polar graph of, the frequency of 3.5 and a little bit with an offset of 2, right? And then we add this to every frame in this, and we end up with this, because it added them all. Now, you'll notice back here, okay, the swish that we made up here was an oscillator with 500 iterations. That means there's going to be 500 vertices in the swish frame. But when we generated the polar thing, there's 50,000 iterations in that. And the way that you can add these, LaserBoy adds these things together, is it uses linear interpolation to find a point along any of the vectors in a frame. And by that, okay, there's an example also in the example text folder called compound to higher count. And basically what that means is LaserBoy looks at the number of vertices in this frame, the number of vertices in this frame, and says, well, this one has more in it than this one does. So we're going to have to linear interpolate to pull positions out of this one to match up with all the XYZ coordinates that are in this one. And to demonstrate that, well, I'll just open this and I'll show you what it does. Okay, all right, there. That's the unit circle, right? This is the first frame, and it is a perfect isosceles triangle, and it has 4 vertices in it. 1, 2, 3, 4. And that's it. This is a single vector, okay? So there's the triangle, the square, pentagon, hexagon. Okay, it goes up all the way up to a 10-sided, a 12-sided, because there's 13 vertices, a 12-sided polygon. But like I said, this is a single vector right here. So then also in this file, and I can show you how this was done, by the way, right here all we're changing is iterations. We're drawing the circle. You remember we started with, a starting point of 0, a duration of 1 full cycle around the unit circle. We want exactly 10 frames in this when we call the animated generator, which is right here. And the first frame has 4 iterations, which is the perfect triangle, and the last frame has 13 iterations, which is the 12-sided figure, the dodecagon it would be. All right, so then we just step through 10 frames and we get 10 perfect polygons in a row. So we render that in yellow, by the way. All right. Oh, we also, before we render it, we blow the whole thing up by 5. We multiply both x and y coordinates of every vertex in the set by 5 and scale it. See, there's no leading or trailing underscore. It's simply scale every frame by this factor. So that's what we just did, and then we rendered it. Now that's what's in LaserBoy space. And then we did a duration of 200, which means 200 times around the unit circle and iterations of 4,000. So there's going to be 4,000 vertices in this frame, which is going around the circle 200 times. And see here, we're calling oscillator XY, which is the same as the Lissajou. Remember I mentioned that. All right, so it's just drawing 200 circles in 4,000 iterations. And this, as we mentioned earlier, right here, there's only 4 vertices, 4 iterations of the function, 13 iterations of the function, right? Which is a circle, but we're getting a polygon because we're only calculating this many points around the circle, right? Now there's this many, and then when we add them together, which is exactly the same function that we used in the turkey thing to do the whoop thing, right? Then we color the result of that magenta, and we render it. So this is just around a circle. As a matter of fact, I'll go ahead and render it right there. And whoops. Make it green. Back to here. And alright, there's our polygons with just a handful of vertices in each one. Alright, and then this is, I'll show you. There's, 200 times around. Yeah, 200 circles piled on top of each other using 4,000 vertices to do it. Looks like, well, it looks like this if you stretch time in Z. It's actually, it is actually just a circle, okay? And then there's the sum. Remember, we added we had the polygons, then we added that circle thing around the unit circle thing, and you can see that along this, which is a single vector in the first example where it's in yellow, where it just shows you this polygon, it's a single vector from here to here. LaserBoy has found all of these points along that vector to be the center of this circle as it's moving along. So that's how compound to higher count actually works. And as a matter of fact, the reason I called the script language liquid math is because it's all based on double precision floating point numbers, which have pretty astounding numeric accuracy. It's at least 64-bit representation in the floating point unit of a processor. And so the whole language is based upon the concept of interpolation from here to here using real numbers. So from this value to this value over a set of whatever it is, whether it's a set of vertices within the frame or the set of frames within the frame set, what have you. It's some sort of interpolation between an initial and a final value. So it's fluid, it's liquid. So that's why I called it LaserBoy Liquid Math. And I've been trying to, it's weird, but it got as complicated as it is because C++ actually, the implementation of it in C++ and the way that it works sort of organically grew out of simpler ideas, and it became what it is now because as I work with C++, it is such a highly ordered, highly structured language that basically if I say, okay, I'm going to do something this way here, all of a sudden I realize, well, then all of these other parameters and all of these other issues need to be, can be addressed in that same way. So it just grew into what it is now. And I hope that other people who watch these videos actually take an interest in this scripting language and experiment with it. Download the current version of LaserBoy and look at the documentation and look at the example text files and read through it and try to get it and work with it and then you can try to contact me if you have questions about it. And I'm on social media. I'm on Facebook. I'm in the Photon Lexicon. You can contact me through laserboy.org. There's a lot of ways to get a hold of me, and if you want to work with it, come up with questions or suggestions, contact me. Then it'll make it better because it always does. Whenever I collaborate with other people and work on this stuff, all kinds of things are pointed out that I never would have thought of, and then I can fix that stuff and make it better in the future. So anyway, there's all of that, and see you next time.